Hello, everyone, and welcome back to DataMindAI Professional Series on Snowflake. I'm Ahmed Mahmoud, Principal Data and AI Engineer, and today we'll continue our journey on Snowflake architecture, and we'll focus on the Snowflake storage layer. Let's start the journey. Let us go deeper into storage layer because understanding how Snowflake stores data is crucial to understanding its performance advantage. First, columnar storage. Snowflake organizes data in compressed columnar format, which is optimized for analytical queries. When you query specific columns, Snowflake only reads those columns, not entire rows. This dramatically reduces I/O. Second, automatic encryption. All data is encrypted at rest using AES 256 strong encryption automatically. You don't need to configure this, it is built in. Security is not optional, it is fundamental in Snowflake. Third, micro-partition. This is where Snowflake storage gets really interesting. Your data is automatically divided into immutable micro-partitions, each between 50 to 500 megabytes. These micro-partitions are the secret in Snowflake query performance. They are immutable, meaning once written, they never change. Fourth, metadata management. Snowflake maintains rich metadata about each micro-partition, which is min, max value, distinct count, data distribution. This metadata enables aggressive pruning. Snowflake can eliminate entire micro-partition from query scans without touching the actual data. Fifth is time travel. Snowflake maintains a historical version of your data for up to 90 days. You can query data as it exists at an early point in time, recover from accidental deletion, or compare data across time period. And finally, failsafe. Beyond time travel, there is an additional 7-day recovery period for disaster scenarios. This is Snowflake's safety net for data protection. Together, these features create a storage layer that is secure, efficient, and incredibly resilient. Now, let us look at the storage layer in Snowflake, the foundation of how Snowflake stores and manages your data. It is hybrid columnar storage. Snowflake uses a hybrid columnar storage format, which means that although data is written as logical rows, it is stored physically in a columnar layout. This gives you the best of both worlds. Fast analytical queries because columns compress extremely well, and efficient storage for all the data types. Automatic micro-partitioning. All data in Snowflake is automatically broken into micro-partitions, typically around 60 megabytes in size when compressed. You don't manage partition manually. Snowflake handles it for you. These partitions include rich metadata, which allows Snowflake to prune unnecessary data during queries, dramatically improving performance. Optimized for semi-structured data. The storage layer is also optimized for semi-structured formats like JSON, Avro, Parquet, and ORC. Snowflake automatically extracts attributes, build metadata, and store them in a way that makes querying semi-structured data just as efficient as querying relational tables. In summary, in Snowflake storage layer, data is stored efficiently, partitioned intelligently, and optimized automatically, giving you high performance without the need for manual tuning or maintenance. One of the most important innovations in Snowflake architecture is the use of micro-partitions. These are small contiguous units of storage that hold your table data, typically between 10 and 16 megabytes in compressed size. What micro-partitions are. Instead of storing an entire table as a single block, Snowflake automatically breaks the data into hundreds or even thousands of micro-partitions. Each micro-partition covers a subset of rows which are stored internally in a columnar format for maximum compression and fast analytical performance. Many micro-partitions per table. A single table can contain a very large number of micro-partitions. The benefit is massive parallelism. Snowflake can read only the partitions needed for a query rather than scanning the whole table. Micro-partitions are immutable. As we said before, one key property is that micro-partitions are immutable. Snowflake never updates them in place. Instead, when data changes, such as insert, delete, or merge, Snowflake writes new micro-partition and marks old ones as invalid. This is how Snowflake enables time travel and fail-safe without performance penalties. Rich metadata for optimization. The service layer automatically stores rich metadata for every micro-partition. This includes min and max value for every column, distinct count, estimates, null count. This metadata makes micro-partition pruning possible. Snowflake can skip the entire chunks of data during a query because it knows exactly where values fall. So micro-partition summary gives Snowflake its speed, efficiency, and the unique ability to scale effortlessly. They are small, immutable, metadata-rich blocks that allow Snowflake to prune unnecessary data, minimize storage, and process query at lightning speed. Micro-partition. One important characteristic of Snowflake micro-partition is that Snowflake preserves the natural order of the data as it's loaded. Snowflake keeps rows in arrival order. Snowflake does not reorder rows during ingestion. Instead, it writes the records into micro-partition in the exact sequence they arrive from your input files. Example of natural order. In this example, we are loading monthly sales data. The row for January comes in first, followed by February, and then March. Snowflake stores these rows in micro-partition in this order. Why this matters? Preserving the natural order helps Snowflake efficiently prune micro-partition during queries. If you frequently filter by date or month, Snowflake can skip entire micro-partition instead of scanning the whole table, dramatically improves performance. So the key takeaway here is, as data is loaded, Snowflake maintains the natural order of the records inside the micro-partitions. This behavior improves pruning, speed up queries, and keep your table organized in a predictable way. Snowflake not only preserves the natural order of data as it arrives, but it also reorganizes how that data is physically stored inside micro-partition to optimize performance. Data loaded in natural order as raw data arrives, whether from files, streams, or ingestion pipeline. Snowflake writes the row into micro-partition in the same sequence they were received. In the example here, the January row came first, followed by February, and then March. Column data stored together, but inside each micro-partition, the Snowflake stores data in a hybrid columnar format. That means all the value for each column are stored together. So for January micro-partition, you will see all the month's value group, then all the last names, then all the order totals. Example of columnar storage. For January, the month column contains John. The last name column stores Wiggins, Brown, Nguyen, and the total column stores all three numerical values together. The same pattern repeats for February, March. Each month forms a separate micro-partition, and within that partition, the data is neatly organized by column. Why Snowflake does this? This columnar storage model reduces the storage footprint and dramatically speeds up query. When Snowflake now knows that all January values are together, it can prune entire partition and read only the exact column needed for the query. This is one of the core reasons Snowflake queries are fast. So Snowflake preserves the natural raw order when creating micro-partition, but stores the internal data in highly optimized columnar layout. Snowflake does not break your tables into micro-partition. It also collects rich metadata about each micro-partition. This metadata is one of the key reasons Snowflake queries are fast. Natural ordering during load. As new data is loaded, Snowflake preserves the natural order of the incoming rows. In the example on the left, the January row arrives first, and then February, and then March. Snowflake rewrites each group into separate micro-partition. Column data stored together inside each micro-partition. Snowflake stores data in a columnar layout. All the mass value for that partition are together. All the last names are grouped, and all the totals are grouped. This allows Snowflake to compress the data efficiently and scan only the columns needed for a query. Metadata collected for each micro-partition. On the right, you can see the metadata Snowflake capture automatically. For each micro-partition, Snowflake stores minimum and maximum value, distinct count, null count, value range for each column. This metadata is incredibly powerful because it lets Snowflake skip entire micro-partition during query. How metadata reduces scan time. Take the January partition, for example. Snowflake knows the minimum and maximum value for month, last name, and total. If a query filter for February or for totals above 3,000, Snowflake instantly knows the January partition does not match, so it does not scan it at all. This process is called micro-partition pruning. It dramatically reduces the amount of data Snowflake needs to read. So Snowflake organizes your data into micro-partition, stores the columns together for high performance, and collect metadata for each partition to make pruning ultra efficient. This combination is a major reason why Snowflake queries are fast, stable, and effective. One of the fundamental biggest performance advantage comes from micro-partition pruning. Pruning is the ability to skip large chunks of data entirely during a query. And here is where we are running a very simple query. For example, select everything from cells where month is equal to May. Even though it is simple, Snowflake will not scan the whole table. Instead, it looks at the metadata stored inside each micro-partition. Each micro-partition has min and max metadata, so each box on the screen represents a micro-partition. So every partition, Snowflake knows the minimum and maximum value of each column, in this case, the month. Pruning logic. Snowflake looks at each micro-partition and asks a simple question. Is it even possible for this partition to contain rows where month is equal to May? If the answer is no, Snowflake skipped it. So for a pruned partition, January, which is minimum and maximum, both say Jan, skip it. February, skip it. March, skip it. And so on. So every partition that does not include May in the minimum and maximum range is eliminated instantly without scanning the actual data. Only May partition is scanned. The only partitions that survive pruning is the one where the months min and max are both May. Somehow Snowflake scan just that one micro-partition. This can turn a scan of millions of rows into a scan of only a few thousands or even a few hundreds. So number 6, result massive speed and cost. Micro-partition pruning is one of the core reasons Snowflake queries run quite quickly and cheaply. Instead of reading the entire table, Snowflake reads only the partition that are relevant, often less than 6% or 5% of the data. As we said before, Snowflake divides a table, like sales table, for example, into pieces, and each piece 50 to 500 megabytes. And those 50 to 500 megabytes are partitioned in micro-partition. So when the data arrives, it will be registered based on the time it arrived. For example, January data will be there first, and then if there is February and March and so on and so forth. And then it also registers metadata, for example, the min and max of that specific data in that specific micro-partition. And then when you try to query the data, like here, for example, select everything from a sale where month is May. So Snowflake would look first on the first part, the first partition. It is January, it's not May, so it will ignore it. And then second one is April, it will ignore. So everything will be February, March will be ignored, April will be ignored, and then you'll say May. It will choose May and then give you the data where the sales amount is the one we see in the slide. This slide shows how Snowflake uses micro-partition metadata to determine which partition might contain the last name Thompson and which can be skipped entirely. So the query is, as you can see, select everything from cells where last name is equal to Thompson, and we are looking for a single last name, and Snowflake wants to avoid scanning the entire table. So how Snowflake decide what to scan? So each box on the scan represents a micro-partition, and for each partition, Snowflake skips the metadata that include the minimum and maximum last name value stored inside that partition. Yeah, if Thompson alphabetically falls inside the partition's min to max range, the partition is a candidate and cannot be pruned. However, if it falls outside that range, Snowflake immediately eliminates it. So let us walk through this slide on how this operates. So, for example, when you see the first one, the January partition, you see that the last name ranges from Brown to Wiggins, yeah, as you can see there. So therefore, Thompson fits alphabetically, and thus Snowflake keeps that record. However, when you see April, Clark, but the partition is from Clark to Patel, then Thompson is outside the range, and therefore Snowflake pruned that one. The July partition is Adam to Wang, so Thompson fits inside that one. As you can see, W is after T, and therefore Snowflake skipped that one. And then you have October partition, which is almost to Yamamoto. So as you can see, the Y is after T, and therefore Snowflake keeps that record as well. Now, if you look at the middle rows, which is February partition, the W is also after T, and therefore it will be kept. The May partition, though, is beginning to say, and therefore Thompson is alphabetically after to say, as you can see, TE, and then Thompson is TH, and practically it is after TE, the TH, and therefore Snowflake pruned that one as well. If you go August, you can see that the V is after T, and therefore Snowflake keep that record. November partition, the H does not fit. Thompson does not fit because H is like before T, and therefore November partition will be pruned. If you see the final row, which is March partition, the Z is after T, and therefore Snowflake keep that record, that partition. And if you see like the V is also after T, and therefore it will be kept, the partition is kept. And also September is the Z is after, or Z is after T, and therefore Snowflake keep that one as well. So in summary, you can see that every light blue partition remains a candidate because Thompson falls within the alphabetical last name range stored in its metadata. Every orange or X partition is eliminated immediately because Thompson cannot possibly exist there. This saves Snowflake from scanning large portions of the table, even though the query itself is extremely simple. And in a nutshell, micro-partition pruning allows Snowflake to eliminate irrelevant partitions using metadata only. No data scan needed. This drastically improves performance and reduces cost. Now, let us talk about why Snowflake storage is so incredibly efficient. The numbers here are impressive and have real business impact. At the top, you see the formula 10 to 15 times compression plus 90% query pruning equals massive cost savings. Let me break this down. Automatic compression. Snowflake achieves 10 to 15 times compression ratio on average through its columnar storage format and best-in-class compression algorithm. And this happens automatically. You don't tune compression settings. A terabyte of data might only consume 70 gigabytes of storage. Micro-partition pruning. Through metadata we discussed earlier, Snowflake can eliminate 90% or more of micro-partition from query scans. If your query filter is on a date column, Snowflake knows exactly which micro-partition contain that date range and only scans those. The rest are pruned away before any data is touched. Now let us look at the 4 key features that drive this efficiency. Automatic compression applies the most efficient compression algorithm based on your data characteristic. String columns might use dictionary compression, while numeric columns use different techniques. Micro-partition pruning uses the metadata we discussed to eliminate scanning irrelevant data blocks. This is why probably designated queries run so fast in Snowflake. Clustering key allows you to organize large tables for optimal pruning. By defining clustering key on commonly filtered columns, you improve pruning efficiency even further. Zero copy cloning is perhaps the most impressive feature. You can clone entire database instantly without duplicating storage. The clone shares the underlying micro-partition until changes are made. This is perfect for creating development environment, testing data pipeline, or performing what-if analysis. The combination of these features means you store less, scan less, and pay less while getting better performance. Let us briefly talk about this Apache Iceberg, an open table format that is becoming increasingly important in the data platform ecosystem. So what is Apache Iceberg? It's an open table format designed for huge analytic data set in data lakes. Think of it as a layer that sits on top of your data files in cloud storage, providing database-like capabilities, which is ACID transactions, time travel, and schema evolution for data that lives in open format like Parquet. And what it is like, the data lake stores data in files, and then on top of that file, you have this Apache Iceberg. And this Apache Iceberg brings like ACID capabilities to your data and time travel as well as schema evolution. So let me highlight 6 key capabilities in here for Icebergs. One is universal compatibility. Iceberg works with Spark, Flink, Trino, Presto, Hive, Snowflake, and many other engines. So write data with one engine, read with another. This is interoperability is crucial in modern data platform. So it is universal compatibility, and then you have efficient metadata. So Iceberg uses a tree-based metadata structure that makes query planning extremely fast, even with billions of files. Traditional approach that uses file listing becomes impossibly slow at scale. So you have this, as I said before, ACID transaction. Iceberg provides serializable isolation for transactions. Multiple writes can modify a table simultaneously without conflict or corruption. This is critical for reliable data pipeline. Time travel and rollback, like Snowflake, Iceberg maintains snapshots of your data. You can query historical states or roll back to previous version if something goes wrong. Hidden partitioning. Users don't need to know about partition schema. Iceberg handles partition evolution automatically. So a schema evolution, which is add columns, rename fields, or change data types safely without rewriting your entire table. Iceberg tracks schema changes and handles them gracefully. We are going to look at all these functionalities or these features when we go to the demo within the Snowflake. Just here, I want to mention here is like Snowflake also support Apache Iceberg, and you can use that file format or table format in Snowflake. That is the whole idea here. So, in a nutshell, Snowflake has embraced Apache Iceberg with native support, combining Snowflake performance with open table format flexibility. So Snowflake now offers native Iceberg support, which means you get the best of both worlds. Snowflake's powerful query engine and optimization capabilities combined with the Iceberg open format and interoperability. Let me explain the key integration point. External Iceberg tables. You can read Iceberg tables that are stored in external cloud storage like S3, Azure Data Lake storage, or Google Cloud Storage. The data stays where it is, but you can query it through Snowflake with full SQL support. So you have external tables in different storage area like AWS S3 or Azure storage, and you can query it using SQL within Snowflake. And you have these managed Iceberg tables, which is Snowflake can also manage Iceberg tables completely, handling both the metadata and storage. You get full ACID transaction support, just like native Snowflake tables, but in the open Iceberg format. Then you have catalog integration. Snowflake connects to external Iceberg catalog like AWS Glue catalog, REST catalog, or the rest. I mean, the different catalogs. Yeah. So this means your Iceberg tables can be discovered and accessed from multiple platforms. Interoperability. This is a game changer. You can write data in Snowflake and read it in Apache Spark, or write in Databricks and read it in Snowflake. So the data is accessible from any Iceberg-compatible engines. This breaks down data silos and enables true multi-platform architecture. So performance optimization. When you query Iceberg tables through Snowflake, you still benefit from Snowflake Query Optimizer, caching, and execution engine. You are not sacrificing performance for openness. This Iceberg integration represents Snowflake commitment to open standard and interoperability. You are not locked into a proprietary format. Your data remains accessible from any tool that supports Iceberg. Now, we saw before Iceberg, and there's also another approach, which is Delta Lake, which is you can find it in Databricks as well as in Microsoft Fabric. So you have the data lake, which is like which stores files, and you have structured or unstructured as well, data lake, and then on top of that, on top of the data lake, there is this functionality which makes the tables look like a database, like it supports ACID transactions. So the data lake and the Iceberg have a lot of similarities, and therefore I thought it was very useful to compare the two, which might be useful to understand why we have Iceberg and why we have a Delta Lake in the first place. So let us start with the origin and the governance. So you have the Iceberg was created at Netflix in 2017, and it is governed by Apache Foundation, making it truly vendor neutral, while the Delta Lake came from Databricks in 2019, and it's governed by Linux Foundation. Though Databricks remains the primary contributor, so both are open source, but the governance models differ. So you have this engine support. This is significant because Iceberg was designed from day one for broad engine support like Spark, Flink, Trino, Presto, Hive, and now Snowflake, while Delta Lake was initially optimized for Spark and Databricks ecosystem, though support for other engines is growing. Now you have partitioning. Iceberg offers hidden partitioning, meaning the table handles partitioning automatically, and users don't need to think about it. Delta Lake requires explicit partitioning, where users must specify partition columns in their queries. This makes Iceberg more user-friendly and less prone to error. And then you have this metadata structure. This is crucial technical difference. So Iceberg has a tree-based, highly efficient structure, while Delta Lake have like JSON transaction log. And then you have this time travel. The time travel both support time travel, but differently. Iceberg uses snapshot-based time travel with unlimited retention. You control how long to keep a snapshot. Delta Lake, on the other hand, uses transaction log-based time travel with the default 30-day retention, though this is configurable. Neither format is inherently better. The choice depends on your ecosystem. If you have heavily invested in Databricks and Spark, Delta Lake is a neutral fit, or natural fit as well. If you need broad engine compatibility and are building a truly open lakehouse, then Iceberg offers an advantage. Let us wrap up our deep dive into Snowflake architecture and the storage layer with the key takeaways. You should remember, under Snowflake architecture excellency, 3 points are crucial. First, the three-layer architecture with independent scaling of storage and compute is Snowflake's fundamental architecture advantage. This separation enables cost optimization, performance isolation, and operational flexibility that traditional architecture simply cannot match. Second, storage efficiency through this 10 to 15% compression, intelligence micro-partitioning, and 90% query pruning means you store less, scan less, and perform better. These are not just nice features, they translate directly to lower costs and faster queries. Third, the cloud services layer provides seamless management and continuous optimization. You benefit from database class features without database administrative complexity. Under Iceberg and Open Tables format, first, Apache Iceberg provides a vendor-neutral, high-performance table format for data lakes. It brings data warehouse capability, asset transaction, time travel, schema evolution to open file format. And second, Snowflake's native Iceberg support enables true multi-engine interoperability. Your data is not locked in a proprietary format. You can use the best tool for each job while maintaining a single source of truth. Third, Iceberg excels in metadata efficiency and multi-engine compatibility compared to Delta Lake. For organization building open multi-platform data architecture, Iceberg offers significant architecture advantage. Looking ahead, in our next episode, we will dive deep into Snowflake's feature and capability from Snowpipe and streams to Cortex AI governance and performance optimization. We'll move from architecture to practical capabilities. Thank you for joining me in this deep dive into Snowflake architecture. I'm Ahmed Mahmoud from DataMindAI, and I will see you in the next episode. For more data engineering and AI content, visit datamindai with ahmed.com.